This is important since, based upon the Job 28.9 concept, we're not really interested in uplifting flat horizons, but pre-existing folds. Using the shear mechanism just described, this figure shows how a pre-uplift fold train will respond to an asymmetrical uplift located in the center of the fold train, thereby forming the post-uplift deformation. Notice that the pre-uplift fold frequency increases from top to bottom, with the same uplift applied to each fold frequency. It is obvious that as the fold frequency increases, the uplift deformation becomes more interesting. Of particular interest is the uplift deformation associated with the high frequency folding at the bottom of the figure. Let's take a closer look. Notice that at this particular frequency, generalized forms of key structural elements commonly associated with uplift tectonics become apparent. The compressed folds on the right are reminiscent of high-angle frontal thrusts associated with the deep frontal basin. The stretched folds on the left are reminiscent of the low-angle back thrusts that occur on the backside of major uplifts within the elevated back basin. In the following comparisons between model and field data, we will examine these similarities in greater detail. In these comparisons, non-faulted simple wrench folds have been overturned using an asymmetrical uplift. In this first comparison, a simple uplift model is compared to the Uinta uplift cross-section shown earlier. The Uinta cross-section was used to describe key elements of a basin and range province. For the sake of comparison, the model cross-section has been truncated in the shallow section. Notice that the Job 28.9 concept applied to simple, non-faulted transpressional folds produces a cross-section which exhibits the key elements of a basin and range province. Both the geometry of the overall uplift and the bed thinning is reproduced in the model. The next comparison takes a closer look at the bed thinning associated with the frontal thrust adjacent to the deep frontal basin. Based upon the uplift mechanism of constant volume and intergranular shearing, significant changes in bed thickness are to be expected in overturned clastics. In this comparison, the well control indicates that the basinal Paleozoic section of the Laramie Basin in Wyoming thinned significantly beneath the frontal Arlington thrust. Uplifting a simple wrench fold using a shear angle of approximately 40 degrees produces a similar thinning in the truncated uplift model. Again, as a result of bed shear, as the bed thins, it elongates, thereby conserving sediment volume. If the uplift mechanism is correct, the Precambrian basement is not block faulted upward as traditionally viewed, but rather micro-sheared upward in the same manner as the sediments. Evidence of shearing should be present in the microfabric of this granite. For the next comparisons, we will move to the Wichita uplift area shown earlier. Along the Wichita uplift, the Anadarko can be considered a deep frontal basin, and the Hardman Basin to the south an elevated back basin. Notice that the thrust symbols for the bounding faults on each side of the uplift point in opposite directions, similar to the asymmetrical Uinta uplift. The map also shows the location of a CoCorp deep crustal seismic line. A deep geologic interpretation based on this line is shown below the map. Talking from personal experience, the mountain front section on the Anadarko side of the uplift is NR, or no reflections, on seismic data, since the structural dip of the overturned section generally exceeds 50 or 60 degrees. The mountain front interpretation does display a basement overhang in red, which is underlain by Paleozoic sediments in orange. Since the structural dips are less on the back side of the uplift, the seismic quality should improve along with the interpretation. An interesting part of the seismic interpretation is the possible existence of what Brewer calls a very old basin south and partially underneath the southern flank of the uplift. The interpreted sediments are shown as stippled orange in the cross-section. Their existence has not been tested by the drill and is based solely upon a seismic character more consistent with layered sediments than igneous basement. Using large, high-amplitude wrench folds combined with a regional asymmetrical uplift, a model of the Wichita uplift was created. Unintentionally, the uplift parameters were chosen such that the overturned clastic section in front of the mountain front was actually thickened. Also of interest is the clastic section it produced beneath the southern flank of the uplift, supporting the CoCorp interpretation. The final comparison shows that small-scale features, such as individual fields, can be modeled as well as large regional features. The Carter-Knox field is an elongated, wrench-related field located southeast of the major uplift area along the frontal Wichitas in an area of diminished uplift. Its approximate location relative to the major Wichita uplift is shown on the map. A cross-section through the Carter-Knox structure at the bottom of this figure reveals a strange-looking asymmetrical anticline. This structure has been an enigma to me for some time, since I was taught that the pop-up looking structure was a result of horizontal thrusting, even though I felt the shape was inconsistent with horizontal stress. I feel the Job 28.9 uplift concept has provided me with a better explanation for the strange asymmetrical shape of this field. Again, uplifting a relatively simple wrench fold using a mild asymmetrical uplift creates a first pass model structure which is similar to the field structure. It is interesting to note that the first pass model predicts the presence of a deeper subthrust structure, which was a deeper pool discovery at Carter-Knox. Finally, it is interesting how the orientation of the extremely thin strata in the model